Hello, my name is Haider Manuel Padilla Prada. I'm presentation this exercise. Y double prime plus fx y prime plus q x y equals to fx. Yp is equal to u1 multiplied by u1 plus u2 multiplied by u2. Who do we find u1 and u2? Using the Gaussian, and we are left with this form. U prime 1 equals to u1 divided by the w. U prime 2 equals to w2 divided by w. We take the integral of u1 and u2 and we are left with the following. u1 is equals to integral the w1 divided by w, and u2 is equal to integral the w2 divided by w. The Gaussian is a w is equals to y1, y2, y prime 1, y prime 2, w1 is equals to 0, y2, fx, y prime 2, w2 is equals to y1, 0, y prime 1, and fx. We find the discriminant, which is a 0, and we find case 3, which tells us that they are conjugate complex roots. After knowing that they are complex roots, we solve the characteristics polynomial. N squared minus 2m plus 2 equals to 0. Using the quadratic formula, we have that m equals to minus b plus or minus a square root of b squared minus 4 multiplied by a multiplied by c divided by 2 multiplied by a. Replacements, and we are left m equals to minus multiplied by minus 2 plus or minus a square root of minus 2 squared minus 4 multiplied by 1 multiplied by 2 divided to 2 multiplied by 1. Then we are left with n equals to 2 plus or minus square root of minus 4 divided by 2. Then n equals to 2 plus or minus 2 multiplied by I divided by 2. The result is m equals to 1 plus or minus I, where 1 is alpha and I is beta. By means of the formula of CAF3, the complementary solution will do yc equals to Euler alpha x parentheses c1 cosine beta x plus c2 sine beta x. Then we are left yc equals to c1 Euler x cosine x plus c2 Euler x sine x, where Euler x cosine x is a y1 and Euler x sin x is a y2. We calculate the worst-can. W parenthesis y1 y2 is equals to Euler x cosine x, Euler x sine x, Euler x cosine x minus Euler x sin x, and Euler x sin x plus Euler x cosine x. Multiply and we are left with W is equals to Euler 2x. Now we do the worst-can for W1. Then W1 is equals to 0, Euler x sine x, Euler x secant x, and Euler x sine x plus Euler s cosine x. We solve and we are left with W1 equals to minus Euler to x secant x and u sine x. Now W2 is equals to Euler x cosine x 0, Euler x cosine x minus Euler x sine x, Euler x secant x. Then W2 equals to Euler 2x cosine x secant x. In the worst case, we multiply in x. We apply the formula and we are left with u prime 1 is 2 equals to minus Euler square x secant x sin x divided then Euler square x is equals to minus secant x multiplied by sin x, and then is equals to Euler prime 1. Now Euler prime 2 is equals to Euler squared x multiplied by cosine x multiplied by secant x divided then Euler 2 Euler squared x. We do the operation and we are left with u prime 2 is equals to cosine x multiplied by secant x. Ready. Now the integral for u1 is equals to integral minus secant x sin x dx equals to minus integral the 1 divided cosine x multiply sin x multiply dx is equal to minus integral tangent x multiply dx. Then we are left with u1 is equal to natural logarithm parenthesis cosine x. The integral for u2 leaves us u2 equals to integral cosine x secant x multiply dx equals to integral the cosine x multiply 1 divided cosine x multiply dx equals to integral the dx. Then u2 we are left x is equals x. The overall solution is yp is equals to u1 y1 plus u2 y2, uh, then yp is equals to natural logarithm parenthesis cosine x Euler x cosine x plus x Euler x sin x. Then the general solution is equals to Euler x parenthesis natural logarithm cosine x close parenthesis cosine x plus x sin x. Thanks for watching.